hopefully you've got a good sense now of what I mean by the horse and cart problem. The idea is if a horse tries to pull the cart pushes pulls the horse backwards. Why do those two forces not cancel each other out? Now in the reading, it asks you to think about this as two different systems, and I just kind of want to give you another way of looking at this. So you can go ahead and add this to your notes. So here is my very well drawn horse and cart, and I'm going to define two different systems. I'm going to define the system of the cart, and I'm going to just define the system of the horse. And let's look at what is going on for each of these objects. So what's happening here is, what I'm going to do is I'm going to draw two free body diagrams, and I'm going to do some color coding on my notes that you may not be able to do on yours, but I just think it might be helpful. So this is going to be my free body diagram for the cart system, and this is going to be my free body diagram for the horse system. And I want to be clear, I'm going to ignore, for our purposes here, I'm going to say that there's that the wheel itself has no friction. And I'm also going to ignore all of our normal and gravity forces just to make it more clear what I'm talking about here. So what's happening, right? The horse exerts a force on the cart, right? And that's forward. So what I'm going to do is I'm going to draw this one force, and I'm just going to, instead of calling this the applied force, I'm going to call this the force on cart by horse. That's this force, right? That acts on the cart system. What does the reaction force act on? It acts on the horse. So if we've got, remember Newton's third law, every action is an equal and opposite reaction. So if we have a force on cart by horse, we have a force on horse by cart, right? But notice, you already see why these two things are not going to cancel each other out, right? They're not canceling each other out because they're not on the same system. They're not on the same free body diagram. So they cannot cancel each other out. The only things that can cancel each other out are forces that are on the same free body diagram. All right, but then you might have the follow-up question, which is, why doesn't this horse go backwards? Well, this horse doesn't go backwards because the horse's legs, or the horse's hooves, right, are pushing against the ground. And so we now have a bigger force here that I'm going to call the force on the horse by the ground, right? And that one has an equal and opposite reaction, but I would have to draw that as a separate free body diagram, right? So what I would say is if I drew another free body diagram being the ground, this one has a force going this way that's force on ground by horse. And the ground just has that force on it, right? And let's think about why the ground doesn't move. Remember, the ground has so much mass, and so the ground isn't what's going to move. But look at what I've done here. I have every force has an equal and opposite reaction force, but it's acting on a separate system. And so I can go back here and I can say that the net force of all of these is forward, right? The forward force is always winning, at least on these two. The backward force is winning on the ground. Sorry, this should be horse, and this should be the net force on the ground, right? The backward force is winning on the ground, but again, remember we've got force equals mass times acceleration, and this mass is going to be so gigantic that the ground is not going to accelerate very much. So hopefully this is another way for you to kind of see that while there are equal and opposite forces, the reaction force acts in a, at least in some cases, the reaction force acts in a different system than the action force, and because of that, you can still have a net force. They don't all cancel each other out.